Then it's really simple. What do you typically refer to this direction as being? Clockwise. So this is derivatives. The derivative of the sine is the positive cosine. The derivative of the cosine is -1 multiplied by the sine. If you took the derivative of -1 times sine, you'd get -1 times cosine, etc. So anytime you're working a problem and you want to make sure you don't make an error with the plus or minus, that's pretty helpful. This direction is known as anti-clockwise, hence anti-clockwise, hence antiderivative. Is that okay? I brought that up because the music that was playing, that's actually Susie Lind who is singing. So I think that's.
Oh, really? Wait, play it again.
Seriously.
Wait,
Yeah, she was a student in my class long time ago.
Susie, what you genius.
Okay, cool. A few people as I walked around specifically mentioned that they had gotten through the entire homework, but they did get stuck in a couple of places. We do have kind of various day to day, but today we do have a little time to kind of address a few questions if someone has a specific one that I'd like to say.
Yeah. I think you look at it.
Okay, at number 6, they give you an equation for G. They ask on what intervals will G be concave up. So I remember Danica's chart. Danica's chart says G is concave up when G prime is increasing. So my first thought was I'm going to find G prime, see if that helps. So I need to take the derivative of this integral. So I use our new rule for finding the derivative of an integral. So I grab the integrand, I write it down, I multiply by the, plug in the upper limit, multiply by the derivative of the upper limit, subtract, exact same process with the lower limit. You even want me to talk more about this. All I'm doing is using the rule. It's strictly memorization. Okay? But d of 0 over dx would be 0. So this is gone. Dx would be 1. So I figured out that G prime really is just out. Okay, I've seen a lot of AP problems where that does happen. Please just don't kind of skip this step and assume that it always happens. They'll trap you the moment you do that. So now I say this is really a graph of G prime. So I can analyze the graph and state the following. G prime is increasing for this interval, right here. G prime is also increasing for this interval. Therefore, G must be concave up on those same intervals. Please.
why do you have the greater than or equal to sign for the -4, but then not the 0?
So I can see right here, well, endpoints are a little tricky.
Okay.
And it's a little tricky also, like at this moment, there'd be some controversy as to whether the graph is increasing or already decreasing.
That makes sense.
So they're pretty lenient on that, actually.
Okay.
My thought was, well, I'll just go with, right here, it seems to be increasing. There seems to be no indication of decrease.
Yeah.
So I counted the endpoint. Here it's kind of controversial, so I just didn't worry about it. Does that kind of help?
That makes sense.
Hadley?
So, when they're grading it, say you kind of did a different method, but you got the same answer, are you going to be okay with that?
Just depends.
Well, I did G double prime. I made it a lot more complicated than it should.
Me too. I tried it out a little bit.
I didn't even do it.
Let me comment on that. 2 points. Good question. 1 second.
It's about 6.
I couldn't hear you. Sorry.
It's about 6.
Oh, 1 second. You're good. Let me just answer Hadley's question. All eyes over here. There are going to be quite a few questions in the future where using double prime is going to be the best choice. And we've already had quite a few of those in the past as well, for sure. This one, using G double prime, does get kind of messy and difficult. So I don't know if they give you full credit or not. Would it just easier to use G prime in this case? But it does kind of vary from problem to problem. So please.
I'm just a little confused on the back of the answers. It says that one of the terms is given when you consider G double prime is greater than 0.
Well, wait a second. Let me look at it. Six, right?
Yeah.
Thank you. Oh, I got it. Hold on a second. Okay. In my opinion, the way they answered it is the harder way to do it. You can do it this way. They're basically saying, yeah, like Hadley figured out, G double prime is the same as F prime. Well, you kind of go in a circle here. You end up going G double prime is positive when F prime is positive. I don't, like, we can spend some time and kind of go through and talk about where this comes from, but you don't have to do that. Like what I showed you would get you the full 3 points for sure. I can guarantee
You didn't
it.
write specifically G double
You do
prime.
not. No. Cool. Next one. Other questions that you brought with you, please, Tristan. 14. So it's a limit problem, so I remember the limit flashcard. Theta is not approaching infinity, skip that. Don't really remember any trig identities, so I can't see any way to factor, so I skip that. I'm going to try L'Hopital's rule. First thing is I must do the L'Hopital test. So I plug in the limiting value. Sine squared means sine multiplied by sine, or all of it squared like that. So let's see, the cosine of 0 is 1. The sine of 0 is 0. So the result of my test is 0 over 0, which is successful. Please.
Do you have to show the test when you're out?
No, you can do it in your head.
Okay.
Yeah. 2 points. Anybody else? Awesome. So the next step is to find f prime, meaning the derivative of the numerator, f prime of theta in this case. So I say f prime of theta is going to equal, let's see, the derivative, that'd be the derivative of 1 minus cosine of theta. So that's going to equal 0. See Susie's circle, derivative of negative cosine is positive sine. So this would be, I don't want to mix this up. The minus is causing me grief. So I'm subtracting, the derivative of the cosine is the negative sign, so it looks like that. There we go. So what I said is it's 1 minus the derivative of this. The derivative of cosine is negative sine, so that becomes positive. Here's the circle. So I've got 1 minus cosine, right? So I'm going to go, derivative of 1 is 0. There's my minus. The derivative of cosine is negative sine. Negative negative makes positive. So please.
Can you do the derivative of negative cosine?
That would work as well. The way you think of it then would be to say I'm taking the derivative of 1 plus the negative cosine. Does that make sense?
Yeah.
So then you'd say that's going to be 0 plus the derivative of the negative cosine is the positive sign, and you get the same result. So either way is fine. 2 points for Isaac.
Do you have to write down all this stuff, like
Nope.
the derivative stuff, or can you just move on?
You can just move
I'm
on.
just making sure.
No, keep asking, Hadley. They're good questions. I tend to write a lot in class because I want people to see how I'm thinking. So, pretty good here. Awesome. So then I take the derivative of the bottom. So that's g prime. So that's the derivative of 2 sine of theta squared. 2 is a tag-along multiplying constant. Bring down the other 2. You have sine of theta to the first power multiplied by the derivative of sine of theta. You didn't want me to talk about that.
That was the power rule.
That was the power rule.
It was 2 minus 1 is wrong.
Uh-huh. So bring down the 2. This becomes 2 minus 1. You have the derivative of what was being raised to the power. So.
Can you keep back doing this side?
Right, so then derivative of sine is cosine. So we'd end up with, let's keep going across, I guess. We'd have 4 sine of theta, cosine of theta. 2 for Preston. Other questions? You wouldn't need me to go through any of it again. So now you create the new limit problem.
Wait, I thought the derivative of sine was negative cosine.
So the derivative of the sine is the positive cosine. You're okay. That makes sense.
Yeah.
Yeah, getting the plus and minus mixed up is easy. That's why the Susie circle thing really is pretty helpful. So, okay, so now we create a new limit problem. So we're going to find the limit as theta approaches 0 of 1 minus cosine of theta divided by 2 sine squared of theta. Oh, my brain is not working today. Yes. Oh, sorry, wrong person. I said my brain's not working today. Maya says, would you like a throat lozenge? I'm like, I'm not sure really how that would help, but just in case, sure.
I had to do it
It's all good. Whatever. Okay. So this becomes sine of theta divided by 4 sine of theta cosine theta. Questions? No, that's the limit problem. So now we're supposed to find the limit of that thing, because that's how L'Hopital's rule works. But now these two sine values can legally divide. So we end up with this limit problem. So now when we think about, hey, if theta is close to 0, the cosine of a value that is close to 0 is going to be very, very close to 1. So the limit is 1/4.
Wait, say that again?
So limit means take this expression and figure out what will the value of this be if we plug in something that's not equal to 0 but close. So I say, I don't plug in exactly 0, but I plug in close to 0. Well, the cosine of exactly 0 is 1. So the cosine of something that's almost 0 will be almost 1. 4 times close to 1 is close to 4. Hence, the limit is what for? Point? Question? Please. No, because up here, I noticed that this is factored. This denominator, I've got 4 times sine of theta times cosine of theta. So these two factors can divide out. So I'm going to do this limit product. Oh, please.
Could we look at number 7?
7. In number 7, they tell us that this formula called capital F. Don't talk. Okay, please note, on the AP test, capital F always means something different than small f. So you can't get lazy with your notation and think they're the same. So they declare capital F to be this integral. They want us to find the derivative. So I just use my new rule. I need to find the derivative of this integral. The rule says, just straight memorization, find the integrand, which is right here. Write down the integrand, replacing the variable of the integrand with the upper limit, multiplied by derivative of the upper limit. Okay, points for the whole room. Raise your hand if you can tell me, because this is crucial, why this is dx and not dt. Like, it has to be dx, it cannot be dt. So how do we know that that has to be dx and not dt? Okay, everybody. Let's go Weston.
Because you're using x in the equation and not t, or oh, there's dt up there.
Yeah, that's why people get, no, it's 2 points, it's a good comment. That's why people get mixed up, because there's a t here and there's a dt. There's an x here and an x here. So it is a normal thing to think, well, wait a minute, should I be doing dx or dt?
Okay, so it's just because the swervy thing has an x in it, and that's the yeah.
Let me say something, you're really close. Let me just say it back to you, you're really close. Okay, first of all, the t here and the dt here are temporary. They had to be different than this x because they can't match because they have different meanings. The biggest reason I know this is dx is because I'm taking the derivative of f prime of x. That's why I know it's dx. Because you take the derivative with respect to the input variable. So the input variable is x, the variable that we're plugging in, like we would plug in an x here. We wouldn't put anything in here. Those are temporary variables of integration. So I'm plugging in for x, that's why it's dx, because it's the input variable. If you knew that, give yourself 2. So then I just finished the rule. Same thing again, integrand with the lower limit plugged in, derivative of the lower limit. This becomes 0, this is 1, that's it. Questions? Cool. Okay, we better move on to the new stuff. So grab the green.
Wait,
Please, go ahead.
Did you go to number 9 with all your work? And can I can just take a picture and then look through it later?
You're good.
I just want to, yeah.
No problem at all.
Okay, thanks.
You're welcome. So go to number 1 on the green. You're good. You're good? Cool. Okay, on the green, number 1. Okay, focus. Hey. All right. Let's start reading. Okay, container has the shape of an open right, whoa, that's a lot of words. It's a cone, I'm good with that. Okay. Height of the cone is 10. Please note how slow I read. I guarantee a lot of people get stuck because they skim. Skimming is a great strategy on the reading section of the ACT test, okay? Fair? Like, I know lots of people do really well on the ACT by not even reading at all. They just go work on the questions and kind of look back and forth. It doesn't work here. Like, if problems are of such a complexity, you've got to read and comprehend. Like, okay, I got a cone. The height is 10. The diameter up here is also 10. Water in the container. So this represents the water. So that the height is changing at this rate. Okay, I would probably write something down right now. They just gave me a rate. I want to write that down. So I'm going to write up here on the top, dH over dt. The rate of change of the height is -3 over 10. That to me is easier to comprehend than the words. So, do you need me to talk more about that? Please.
Why did you put DH over DC?
The words say that the height itself is changing. So the height isn't -3/10. The height is changing at this rate, and therefore the symbol dHdt represents the rate at which the height changes.
Why did you go to
I didn't know to put it. I just thought it would be easier to write that than to have to remember these words. That's all.
So I could put like X?
You could have, but because they're talking about the height changing, I thought it would be best to say dHdt. A rate is always a derivative, so the height's changing dHdt. Good question. They give us a formula for the volume. That's fine. I probably box that so I can find it later more quickly. Okay, the next question says, find the rate of change of the volume. Okay, we'll pay tickets for this one, or points for this one. This is the symbol that represents the rate of change of the height. So even if you didn't think of that, that's fine. But use what you've learned here and tell me, just raise your hand. What symbol would you use to represent the rate of change of the volume? Like it's just a simple pattern. If this is the symbol, dHdt, like don't worry about the 3/10. The symbol is dHdt. So using that exact same pattern, what symbol would you write down that would represent the rate of change of the volume? Okay, everybody for this one? Anna Katie?
Would be dV dt.
dV dt. So I'm going to write that down. Always fun to say, dV dt. Okay. How many got it? 2 points. Okay. Question? Awesome. Okay, we're supposed to find that, so my habit is to do this, but that's just me. Just reminds me that that's what I'm looking for. So I'm supposed to find this when h is 5. Okay, and I would box this so I don't forget. Indicate units of measure. In fact, I've never thought of this before. Maybe a good thing to do, so you don't lose the unit points, is go to the bottom of the page, like the bottom of the problem, and write down the units right now.
You say you never thought about them.
I've never thought about making that like a habit, because I'm always looking for ways to like just quickly, easily get points on the AP test. And it's common to just forget that. Like you get so busy doing all the work, you know what I mean? Everyone notices it when you're reading, but then later they forget. So I just thought right now, hey, maybe it would be smart to just write them down.
Which is centimeters? Is that what it is?
Well, slow down. We're looking for dV dt. So the way you figure out the units is you say, what would be units of volume? Think of something simple you've learned, right? Volume is length times width times height. So they're measuring in centimeters, so cubic centimeters. 1 second, Maya, sorry. So the change in volume is going to be cubic centimeters over, what's the change in time? What units are they using?
Hours.
Hours. So, no, just
hours.
It's hours. Just read the symbol. Just read the symbol. dV means change in volume. So volume's measured in cubic centimeters. dt means change in time, hours. So down here I'm going to write cubic centimeters per hour, just so I'll remember. And maybe I even get lucky in the greater. I don't know that they give you points if that's how you write. But anyway. Okay. Please, sorry.
The question was, when you write your answer, can you write dV over dt equals and then write your volume, or do you have to put rate of change in volume?
No, dV dt is great.
Okay.
Yeah, no, that's perfect. I see what you're saying. Gotcha. What you're asking is, when do we have to like define the symbol in English words, and when is it just known? Is that kind of?
Yeah.
Yeah, because they told you that V is volume.
Oh, you can.
You're safe to just know that dV dt is the rate at which volume changes, and no need to tell them.
Or the likelihood of you making it dV over dt or like similar to that, is that like the likelihood of all these equations of doing the same thing?
Like, is it? It's very, yeah, very likely. Is that what you meant?
Yeah, like, it's like 90% chance I'm gonna probably do that. Make it like
Yeah, not a big deal on that one.
that's
That
something I should kind of memorize.
I don't think you'll even have to. Like, I think with just a little practice, it will come natural. Honestly. Yes.
I
Okay.
just didn't know if that's like something you just knew
Oh, gotcha.
because you're smart and I couldn't figure that
It's
out.
not smart, really. It's just experience. That's why I say it's just going to be some experience. You'll be comfortable with it. Yeah, it's not like, yeah. Okay, next thing. All right, this part is new. So look at me. Okay, what we've encountered here is a type of problem we have not encountered all year. Music playing? Sorry, I heard something. Between that and the lozenge, I'm going crazy. Okay, there it is again.
It's your
Oh, you're right. It's feedback because I've got my volume turned on. Hello? Yep. You good?
Yeah, that's another.
Cool. It's getting thinking up there going to the computer coming out the speaker. There's the feedback. There it is. So I turned off the. All right, come back. Come on. Okay, this is a new type of problem we've not dealt with before. It's known as a related rate problem. Make sure your phone's put away, please. It's a related rate problem because they're giving you one rate and they're asking you to find another. Okay, simple idea. Sometimes they'll give you two rates and ask you to find a third. I've never seen four. So, and they've always been rates that are as respect to time. Okay, so the only related rate problems I've ever seen always deal with time. You need it? Okay. There's an acronym. The girl who gave me this one, her name was Savannah Norton.
Why are there no girls? What about dudes? Did you guys not figure this out? No, answers
That's just what happens. The acronym she came up with was RED. The R stands for read the problem and record all of the rates that you read about.
Nope, that's a lot. I don't know how that works.
Read the problem and write down, record, right, all the rates that you read about. So we've done that. As we read the problem, they discussed the rate at which the height is changing. They discussed the rate at which the volume is changing. So we wrote them down. I promise this helps a lot.
Wait, that's not an acronym, though.
RED is an acronym, kind of.
The R
I get that it's not a pure acronym. And it's just meant to help you. If you don't like it, that doesn't offend me. So, but I have found most people find it helpful.
Okay, you're going to say it again.
Okay, so R is record all the rates that you are reading about. So.
Where does the E and double R?
No, just the R. Just the R.
Yeah,
Just the R.
That's why I don't get it.
Okay.
Well, this is a tougher. Remember, I've never had this problem before.
I don't know what I'm
See,
missing.
about 8 years I've used this. Usually I just write it down and people, okay.
I'm also in 61% class, so.
Wait, why is it written in blue?
Hilarious. I don't know. Random. Okay. Wow. It's random. Okay. You're solving a related rate problem. If you remember the idea of red, it does help a little bit. Okay. Some people it helps a lot. So the R stands for rates. The R stands for rates. You got to get all the rates written down. Okay. The E stands for equation. Okay. Now the key part of the equation is this. This rate, think of Danica's chart. Think of Danica's chart. If you have a dH/dt in Danica's chart, this is the rate. That means there would be an amount here that's just the height. That's how Danica's chart works. Fair? The same would be true for volume. You'd have dV/dt in a column of the chart, and you'd have V over here. So kind of two different versions of Danica's chart. Okay, all related rate problems follow this pattern, where they give you a rate, but you're also talking about the associated amount. They give you another rate, but you're also kind of discussing the associated amount. And somehow these two rates are related to each other.
So is that the derivative of that one?
Right. So here's the amount. Derivative of the amount is the rate.
Okay.
Here's the amount,
So
because
like,
derivative means rate of change.
so like you have $6, and that's the rate of getting paid.
Think of it this way. The height of this thing
Okay.
is 10 centimeters, right? But that height is changing at -3/10, so let's write it down. The height is 10.
Wait, it's the height of the liquid.
Oh, fair enough. So right here, the height of the liquid is 5. And at that moment, thank you, Zach. So the height of the liquid is 5 centimeters, right? And at that moment, that height is going down by 0.3 centimeters per hour. So this is centimeters per hour. That's how Danica's chart works. Please, Heather.
So, because you know that, like, relationship between, like, H and DH and V, so, but you're trying to find the relationships between, like, both of those, right?
What you're really doing,
And so you use the equation because you know the relationship between H and V, and so you're just translating it. Oh, okay.
yeah, let me say it back to you. It's perfect. 2 points. Look. Okay. The problem really is all about knowing that these two are related somehow. Okay? They're related by this equation. Knowing that, we can figure out a way that these two are related. That's why it's called related rates.
So H is what was H again?
H is the height.
H is the height. For some reason, the hour. I don't know. That's
H is the height.
And then V is the volume.
V is the volume.
And so we're trying to find they're just connected.
We want to see how the rate of change of the height is related to the rate of change of the volume.
Okay.
There is a bit of common sense involved. If you just picture it,
That's what
as this thing goes down, is the height going to go down? Yeah. As this goes down, will the volume of water go down as well? Yeah. They just don't go down at the same rate. The height goes down by 0.3 centimeters per hour. The volume goes down by something else.
So we're just okay. I don't know. It's just funny. We're trying to why we're trying to find the rate of
Okay. Don't get stuck on that. Here's right. You don't want to get stuck on it. All of this stuff has a practical application, but honestly, you've got to go through a lot of college to get to the point where you go back to this and go, oh, I can see why that is helpful now. It takes a long time, so you have to be patient. We good here? Awesome. Okay, so we wrote down the rates. That's what the R is telling you to do. So we've done that. Equation says you need an equation that relates the amounts. That's why Hadley's comment was so valuable. So I want an equation that relates these two. Okay, here it is. So write that down.
Wait, that relates the amount?
Relates
So
the
V
amount.
H.
You need an equation, always relating the amounts, Hadley. So we find the equation that relates the amounts. Really good discussion today. Anybody else? Okay. The D stands for take the derivative with respect to time of the equation. It's okay. D stands for take the derivative with respect to time of the equation, which means what you would write down is this. You'd go d over dt, because that means derivative with respect to time of the equation. So we d dt the left, and we've got to make sure this line is truly equal to this line. So we d dt the right.
Is this something you just have to memorize?
That's a memorized step. Yeah, that's just memorization. But it goes back to what Hadley said as far as making sense of it. These two amounts are related. Therefore, we can write an equation that has an equal sign, right? And just like we've done all year, we want this line to equal this line. Like we want them, okay, that's, I said that badly, I'm sorry. This line really isn't equal to this, but because this is equal, this is also equal. These two things are the same, right? Now stay with me, Mikhail, you'll see it.
Yes.
So you're comfortable, these are the same, fair?
So is this,
So that means the derivative of v
Yes.
is no different than the derivative of all this stuff.
Yes.
So this is also a valid equation. Go ahead.
Okay.
so we have V, which is the volume, and it's equal to the height because the volume.
The volume's not equal to the height. The volume's equal to this equation.
And that equation, what's that equation giving us?
The volume.
The volume, okay.
So you could take this equation, you could plug in the height and the radius, it would tell you the volume. Anybody else? Cool. Okay, we need to take this derivative. Please note, it's nothing new. Oh, please.
Would you plug 500?
Never. Everyone hear this one? 4 points, so mark it down. It's a really important question. So look over here. Come on, look here. Look, don't miss this. Okay, in any problem you're going to work on the AP test, any of them, prior to taking a derivative, don't ever plug in a number unless the number is known to be a constant. Like it's never going to change. So the question is, as this thing unfolds, this story unfolds, is the height always 5 or is the height changing? Height is changing. So it's illegal to plug in the 5 right now.
So would that mean like technically the height goes with the volume of
The volume's changing too, so we can't plug in anything for V either.
but isn't the volume of the cone technically a constant?
The entire cone, but we're talking about the volume of the water in this problem. So does that make sense? Okay. We need to find this derivative. It's not new. So first thing I'm going to notice is 1/3 pi is a constant. So I just pull that out. So this side is just written as dv over dt. Here I pull out the 1/3 pi. I'm left with the derivative of r squared h. Questions? Keep writing things down. Don't just watch. If you write it down, you learn better. Good? Okay. This requires the product rule because r and h are variables. So I have dv dt equals big parenthesis, second function h multiplied by derivative of the first function r squared plus r squared multiplied by the derivative of h. So that's the product rule. Use that for, of course. Questions?
Why did we use dt again on the bottom?
Oh, because everything is changing
At the time.
per time. So with a related rate problem, I've never seen one ever on the AP test that wasn't per dt. You can invent one that isn't, but they never have. So very good. Okay, keep going. So now I have dv dt 1/3 pi h. This is the power rule. Bring down the 2. The r was being raised to the 2, so now it's r to the first power. You always end by multiplying by the derivative of whatever is being raised to the power. So that's just the power rule. Then it's plus. Hold on a second. Say it again. I couldn't hear.
Would it be 2r with the derivative of 2?
No, the power rule looks like this. 2 points for Hayden. Let's write it over here. Hold on. So the power rule looks like this. Derivative of something to a number is equal to the number multiplied by the something, new exponent, multiplied by derivative of the something. You see it now. 2 points. Anyone else? Cool. Can I erase this?
Yes.
Okay. Okay. All eyes on me again. Come on, look over here. Okay. With related rates, once you've got all the rates written down, once you've got the equation identified, they often give you the equation. I'd say about half the time. The other half of the time, that's fair to not say that that's often. The other half of the time, you could come in 2 points. The other half of the time, it's usually going to be the Pythagorean theorem, is the equation you'll write, or you'll write an equation involving similar triangles, which is really easy because it's just proportions. I have seen a few that use SOHCAHTOA. So.
You want to tell me Pythagorean theorem once again?
X squared plus y squared equals z squared. When we get to it, we'll practice. Okay. We've taken the derivative. Listen. Right triangle trick. We've taken the derivative. Okay, after this, all related rate problems become a puzzle. And they're all solved differently. So there's no way to teach you a method of solving it. All we can do is do lots of examples so you kind of learn different ways to solve the puzzle. Understand? Please.
So R and H, we can't make those just 0, why?
Because they are not 0.
But even if they're if they're 5 or they're 6, the derivative of it would still be 0.
No worries. 2 points.
So
the thing you're
why can't we do that?
The thing you're misunderstanding is this. You've got this cone of water. Okay, come on, look at me. Look. You've got this cone of water, but is that cone staying its shape or is the cone shrinking? The cone is shrinking. So the radius is never one single value. You can take a snapshot of it, and at that moment the radius can be something. But in general, it's just everything's changing.
So when it's rates and things, you just have to keep it up.
When it's rates, you cannot plug in a constant if it's changing it. If you do that, you're describing a different situation. You're saying, oh, it's just this cone of water that never changes. That makes sense.
Yeah.
In which case, dV dt would be just 0, because the change in volume would be 0. It wouldn't be changing.
Because it would be times 0 times 0 times 0.
Yeah. Does that?
Yeah.
Perfect. Isaac.
Okay, I think I'm figuring out. But if every radius is going to be a constant, or if the output of the radius is always going to be a number,
Okay, at any given moment, the radius is some number. Yes, but that's only at a given moment.
So what are we trying to find?
We're trying to find what is the rate at which the volume is changing. How fast is this volume shrinking? That's what we're looking for. We're looking for a rate.
Why do they give us the Why do they give us the
Here's why. Look at me. Come on. The thinking is very good. Brennan, Isaac, 2 points each. It's you're right on track. Listen. He doesn't even have class this period. Okay. Seriously.
No, seriously?
Seriously. The room is empty. He's practicing. Okay. I'm not kidding. I'm not kidding. Okay. Mr. Ducty is awesome. But listen. Oh my gosh. I don't know. No, he doesn't have a class. Maya wants to go check. Go ahead, you can check. It's empty, I promise. There's maybe one person in there. I don't know.
Check.
Hey. Hey, I lost track of the question. Somebody asked something.
I asked what's the point of giving us the height equals 5 centimeters?
Oh, gotcha. Okay, so you got this cone, right? The volume of water's going down, so the cone is shrinking in size. And what happens is the rate at which the volume changes is different depending on the size of the cone. We'd have to spend that would take a while to prove that to you. You're going to have to trust me.
Is that just because it's like...
It's just because of the shape. Like what happens is when the volume's big, as the cone changes, the volume changes quite a bit. When the cone gets really, really small, as it shrinks, the volume changes by less. Because large versus small. Does that
more pressure?
Kind of makes sense, right? Okay. Right?
No, there were like 10 students.
10 students?
No, but they were just doing their homework.
Oh.
I looked in and Rusty wasn't in there.
Oh.
I have no clue where he is.
He's got a tape on.
So
He yells every once in
he's
a while. He's outside the window. Okay.
So yeah.
Oh, I'll have to have him do that sometime. That'd be funny. Just go outside the window and just yell through the window.
If I was a teacher, I'd scare the crap out of me.
Look, come on. Oh, good. Okay, are we okay that as the thing changes, the rate's going to change? Okay, so what they want to know is, as this thing is shrinking, at that instant, when the height happened to be 5, how fast was the volume shrinking? Just at that instant. It's no different when you drive a car. Okay, if you're in a car and you are going faster and faster and faster and faster, right? Can you know at any given instant your speed? Just look at the speedometer, right? But the speed is different at different instants. It's the same thing. The rate is different. Because velocity is your rate of change.
So there will come to a time where the 5 will play.
The 5 comes into play right now. Here's why. Look, listen, the rule was, hey, you can't plug in constants prior to taking derivatives. So right here, we can't plug in constants. We took the derivative, right? We kind of finished taking it. So we're done now. We now can identify different things. This symbol represents whatever the height is at whatever moment we're interested in. Okay, 5. We can figure out the radius here in a second, but that's the radius at that moment. I lost the pen. Did I go crazy? Throw lozenges. Thank you. Look, dr dt means not r. This is not r. It never has been all year. It's always been dr dt, not r. Clear? This isn't r. This isn't time. The symbol dr is, it's never been that, ever. The symbol dr means dr. It's a difference. It's not d times r, it's dr. It's like its own symbol. So don't think of that as r. It never has been, never will be. It's okay. It's not r. It's dr. It's the infinitesimal difference in r. dt isn't time. It's the infinitesimal difference in time. Okay, so they're separate symbols. Everybody clear? Yeah. Okay, so you're not going to put in a number here, but you can maybe put in a number here, because dr dt is some rate. Okay? dh dt, that's not height, that's the rate at which the height changes. We have a number for that.
Yeah. Oh my gosh.
-3/10. Got it? Following? Okay. These are good. You really are asking superb questions. You really are. Pretty good? Awesome. Okay, once you've found the derivative, it's time to plug everything in. But the reason it's a bit of a puzzle is because they didn't tell us the radius. And they didn't tell us the RDT. So if we quit now, we'll get a decent amount of points on the AP test, but
That's good.
and hey, like, don't forget what he just said. I'm dead serious. 2 points. Listen, look, now don't forget what Preston said. we'll practice this a lot. We're getting very close to simply working on the AP test in this class. We have one more kind of day of learning a new idea, and then after that, it's practice. Okay, we're that close. As we practice, we'll pick up a few new ideas kind of here and there, but no ideas that we're really worthy of spending like an entire day alone on. So we just kind of learn a little bit. Okay, look, when you take the AP test, one of the smartest things you can do is you're working along, you know, this is going pretty smoothly. Like we had a lot of questions today because it's the first time, plus we're discovering some things that hadn't quite clicked before. When you get to a point where you're like, oh, I'm feeling kind of stuck, honestly, one of the best things you can do is just move on. Just leave it and say, good enough for now, I'm going to go find some other points, because easy problems are worth the same number of points as hard problems. So I don't want to spend time doing hard problems to get 3 points, when I can spend time doing easy problems and get the same 3 points. Okay? All right. We good? Awesome. So we can plug in H is 5, dH dt is -3/10. We need to figure out R. So we go back up here. Okay, remember I told you that a lot of these, a lot of related rate problems involve similar triangles. Similar triangles, very, very easy. You can see them right there. There's a big triangle. I'm drawing half the cone. So that's the container. This dimension of the container is what? Say it. 10. That's the dimension of the container. Okay? I cut it in half to make a right triangle, because most related rate, not most, some good number of related rate problems involve right triangles. What's this dimension of the container? 5. Good. Okay. Within that, we could draw this one, where this dimension is 5. It's a pretty good drawing. I'm liking it. Sorry, it's not red, Isaac. Okay. This dimension would be what? 2.5. Without a calculator, it's better to use fractions. It's easier. So that's 5/2. Okay. You can confirm that by setting up a ratio. You compare big to little. So this side of the big triangle, 10, compared to this side of the little triangle, 5, has to match this side of the big triangle compared to this side. That's why we knew it was 2.5. The ratio has to be that similar triangle. Please.
Would there be any way to find the radius if there wasn't a right triangle that we could get from the volume container?
I can't really answer that question because it will vary depending on what information they give me. So I don't know. You good there?
So
Okay.
is that
What you've learned about this is the following. The height is always going to be twice the radius. Are you comfortable with this?
Yes.
The height is twice the radius. So now you know down here that instead of typing in the radius, you can just say, well, the height's 5, so what's the radius? No, the height is twice the radius. So half of that, 2.5 or 5/2. So we have something we can plug in for R now. We need to find dr dt. Here's an equation. I think a lot of you can see this. Raise your hand if you can think of something mathematical we can do to create a new equation that will involve dr dt. I'm trying to find dr dt. Just don't do something complicated, just do something simple. What do you do to this equation to create dr dt? Come on, hands. What do you do to this equation to find dr dt? What do we do to this equation, Zach, to find dr dt?
When you take the derivative of both sides.
Perfect. Same as we did before. So I take the derivative of both sides. 2 is a constant. I've just figured out dr dt. 1/2 dH dt is dr dt.
You divided the two.
I divided the 2 over, dividing by 2, same as multiplying by 1/2. Okay, how many knew I was going to do this before we did it? 2 points, okay.
I should make that up.
All right, no throwing shade. Apparently not, I didn't get a very good reaction. My goal was to learn teenage slang and then use it at the right moment, but it didn't
I think it
work.
worked.
Please don't throw shade on, it's not kind.
So,
Hadley can handle it, I know that, I'm not worried about that.
If she's a bright person, she
Oh, Hadley is very bright.
Oh.
What did you say?
He said Hadley's a bright person, shade doesn't bother her.
Clever. Hey, we good? Okay. Just look at me. Preston, come back. Okay, look. Just a little kind of comment on related rates. This one's pretty high on the difficulty scale, okay? Like, it was a good one to do the first time all together to show all the different elements. They're not all this hard, okay? They do follow the same pattern, though. So anyway, here we go. So we type it in. So I say dV dt is going to equal 1/3 pi, parenthesis. The height is 5 at the moment I'm interested in. Oh, look, how easy. 2 times the radius.
5.
5 again, because the radius is half of 5.
Yes.
So 5 times 5. dr dt is half of the dH dt.
That's 3/20.
So 3/20. There you go.
Say that again. Wait,
It's negative.
wait, DRTT is half of.
We figured out that dr dt
Okay.
is 1/2 of dH dt.
DHDT is.
They told us dH dt was 3/10, so hence half of that's 3/20. So Hadley again.
yeah, negative.
But you need me to talk through it again? It's fine.
So it says DHDT is 2 DRDT, which is also the same as.
Right, exactly.
Oh,
Yep,
okay.
perfect, perfect. Pretty good?
Sorry.
Sweet. So keep plugging it in. You say plus. The radius is 5/2 or 2.5. I forgot something. It's a written question. I don't have to work it out. So I am quitting now. So.
I would have quit like 20 minutes ago.
Preston, I feel you.
Thank you.
Wait, you can really stall.
Yes. And at that moment you remember, oh yeah, I gotta have the units, right?
Oh! There it is. I counted that.
That's full credit. Yeah, you stop. The best idea is to stop there. So that's full credit.
If I would have kept going, but I would have completely messed up.
You lose the point.
Would I lose the point even though that's there?
Okay, I don't remember how this one scored. I'd have to look at it, but my best guess is it probably gave a point for getting to here. Okay.
Oh, I'm so sorry.
It probably gave a point for the limits, for the units, and it probably gave a point for this mass. So if you mess up this, you lose one of the 3 points.
But what if I would have gone down the line and started trying to figure that out?
Right, you lose that point.
Would I?
Yes,
Even
you
though-
make a mistake.
Oh,
Yes, if you make a mistake. So you don't do that, just stop.
Oh no, just stop.
Got it?
Kinda, sorta, yeah.
Yeah, I get you kind of sort of.
Class over.
No, my computer does that once in a while.
Well, we have 5 minutes.
Yeah, we got 6. Okay.
That's too short. Ship is puny.
All right, next one. Go to number 2.
Do the equal sliders just get bored and I about stuff like light and soft?
I do think it's great. That's what they come up with. That's what you're referring to. Bizarre. Okay, hey. Focus. We got to get some 6 minutes. Come on. Okay.
Oh, this is.
One comment on this particular homework assignment. I don't want you getting over stressed on it. So do the best you can, get as far as you can. If you can only get started on most of them, that's fine. If there's some you can't even get started on, it's fine as well. Don't over stress. We'll have time next period to kind of talk about it again. So, okay, here we go. Ship A is traveling due west. Look, read slow. So west toward the rock. So the ship's going this way. That's easy to see. They give this speed. Okay, here's a huge hint. In a problem, when they give you a speed or a velocity, in a related rate problem, it's better to think of it just a little bit differently. Make sure this makes sense to you. This ship is moving this direction at 15 kilometers per hour. Therefore, the distance x is also changing at 15 kilometers per hour. Because it's closing. Is that fair? Okay. In a related rate problem, it's better to think of distance instead of velocity. It's just easier. So I'm not going to write down that the velocity of the ship is 15 kilometers per hour. I'm going to write down that dx dt. Dx dt. Now remember, dx dt doesn't mean x. Sorry, Elijah, 1 second. Dx dt means how fast is x changing. Is x getting bigger or smaller? Smaller. So it's got to be negative. So that's the rate at which x changes. It's not x, it's the rate at which x changes. Elijah.
That was my question.
Perfect. Because x isn't growing, x is shrinking. Somebody asked last period if this was negative, because the ship is moving in a negative direction. No. It's negative because x is shrinking. It says the other ship is traveling due north. So the picture's stupid. Ship's going this way. You should have drawn the ship like this. It just floats up. Okay. So the ship is going this way. So this distance is changing at 10 kilometers per hour. Is that distance getting longer or shorter? Longer. So dy dt is a positive.
So like looking at that north is important because you over said negative.
Should we put kilometers per hour on the? I don't usually. I just kind of save that for the end. Okay, come on. Next thing. Let's see. So that's done with the reading. So now we go to part B here. It says find the rate of change. They give you the units, so they don't ask for them. Of the distance between the two ships. So this triangle is changing shape because the ships are moving, right? I don't even like to think about it. It makes my head hurt. Oh, cool. Let's go like this. Yeah, that's actually very good. So the triangle is doing what you just did. Okay. We want to know at the instant when this is 3 and this is 4, just at that instant, how fast is this distance changing? Traditional call that c. Okay. They gave part of it they made easy because it's a 3, 4, 5 right triangle. God bless them, yes. Okay. It's a 3, 4, 5 right triangle. So now we're doing tribute to Isaac. So is that throwing shade?
No, blue.
What'd you say?
Paying homage.
Paying homage? Oh, paying homage.
Also,
Yes.
sarcastic.
It was a bit. Yeah, so if I'm sarcastic, then it's throwing shade. If I'm paying homage, it's not throwing shade.
What the F is paying homage?
Focus. Okay, we got these two rates written down. We need a third rate, dz dt. Because that's the rate we're supposed to find. What? Come on, we're going to speed up just a little bit, but you'll see it. Okay. E stands for what? E. What does E stand for? Equation. It's got it. Okay.
So there's no equation, so we're screwed.
Look. The equation, remember, involves the amounts. So it's a right triangle.
Except I'm not making.
A squared plus B squared equals C squared apparently. Who knew? Why did they teach me C squared? No idea.
Mikhail, you okay?
Yeah.
Okay, look. So remember that, okay, sorry I'm rushing a little bit. I only got 30 seconds. I'm going to keep talking after the bell rings because I want the video to be complete, okay? If you want to stay for just a minute, stay. If you need to leave, you leave. Look. Okay, remember we drew Danica's chart on the last one, and I said, hey, you've got the distance x, but you've also got the rate at which x changes, right? And then you've got the distance y and the rate at which y changes. Well, we're looking for not the distance z, we know that. We're looking for how fast does z change. So just like before, somehow these three are related. The amounts, that's this. By taking the derivative, you find how these three are related. And that's how all related rate problems work. So even though, Mikhail, hey, even though the related rate problems have differences, if you can get comfortable with what Ellie just did.
So do you put like the x squared? Do you put dx over dt and what?
So what we do now, we have an equation, right?
Yes.
We take the derivative of both sides of the equation, just like we did on the last one. So we go d over dt of x squared plus y squared is equal to d over dt.
So if I put a d over dx, we got...
Wrong, because it's with respect to time.
Oh, okay.
Please.
So you can't plug the numbers in together.
Correct. So you've got to finish differentiating first, like Hayden said, then you can plug in numbers. Sorry.
Oh, because you're going to have the dy and the dx left
Right.
from the two of...
Right. If you plug in the numbers right here, you're just taking the derivative of constants. It's going to be 0. That doesn't work because everything's changing. So now, okay, I'm almost there, look. So this becomes, these two things are adding, so I take the derivative of this, that'd be 2x dx dt plus 2y dy dt. That's just the power rule. 2z dz dt. Okay, at that point, you're supposed to solve for dz dt, but you know everything. You know x is 4, right? 4?
4. Yeah.
dx dt is negative 15. So I can go 2 times 4 times negative 15 plus 2 times 3 times 10 must equal 2 times 5 dz dt. Remember, it's a 3, 4, 5 triangle. I just solved for dz dt and I finished the problem. So that puzzle. Oh no, you got to get dz dt alone. Yeah. Just divide by 10. So you just, like Elijah saw, you just write this out again.
This makes way more sense than all the other stuff.
My question is, how do you know the 3?
You're much better with practical things.
Oh, true.
Yeah, you always see things better if there's some kind of story. Well, the reason that happens is normal. Our brains